Hello? Hello? Okay, yeah, it looks like it's working. Hi, it's me. Um, I'm, I'm what? What am I? I don't know. The jury's still out on that one. But I am assigned to help you guys learn how to use MATLAB. This is a weekly online session for you to come. I would, if you guys are unable to do Wednesday nights and would rather another night, uh, let's get that set up quick because I'd really like for you to show up and use me and abuse me. Um, anyway, so I'm going to go ahead and work the problems that I said I would in the announcement earlier today. I am going to use the live editor to do this. Um, just to give you an example of how it functions. So I'm going to work two problems uh, out of chapter 3. Um, one, well, I don't think either one of these. Well, they were assigned, but I changed the assignment, so they're no longer assigned. But I still think you'll get some benefit out of them by watching how I would do these problems. So, and I'm going to make sure I do the right problems this time. I did my 10:30 class just an hour ago, and I told them I'd work problem 4.3 and ended up working 4.4 instead because I am stupid. That's a capital stew and a little pud. Um, okay. Um, so anyway, I am going to begin by putting my comment of which problem I'm working here, which is problem number 3.9 from the 6th edition textbook. And you notice I did that. I made lots of, oh, hey, not, no. Okay, hang on. I'm going to pause. One. Okay, I'm back. I hit the wrong button and stopped the pause, and I just, a whole bunch of issues there. So what happened was the Canvas, not Canvas, Zoom. The Zoom meeting closed because it was inactive. And so I just opened it up just in case somebody pops back in. So it's open. So it'll be spliced together like nothing. I mean, it just went, oof, no time whatsoever. Yeah, cool. Right at farm out. So, oh, anyway, shut up. Get busy. Anyway, so what I did was I made a few more spaces here and then change came up here at this point and then hit click text and that changes it from code to text or we can go back to code. That's only available in the live editor. You can't do that in that other one program. Okay, so here's what we're doing. This is my electronic copy of the textbook. I'm going to work problem 3.9. Very large prime numbers are used in cryptology. Go away. How many prime numbers are there between 10,000 and 20,000? Okay, and then it says use primes and length as a hint. Quit showing that. I don't want to highlight nothing. Okay, so um, this is very easily done. It can be done in one nested loop, or you can do it with several loops creating variables. Which way do you want to see it? Nested. Okay. Okay. Well, I'll do both. So let's do the first group is we're going to find the primes in 10,000. And if you want to see that poof, there is all the prime numbers. Where is all the prime numbers? There's all the prime numbers. There's 1,229 prime numbers between 0 and 10,000. Okay, we're going to suppress that. And then we'll do a second, because this is going to be even more primes of 20,000. And then we run that one, and there's 2,262. So, but we want to know how many there are between this one and that one, so that's where we get uh, the length comes in. We do length of first. No, yeah, let's do second, so it comes out a positive number. Ha ha ha! If I do that, minus the first. And that will tell us how many there are between the two of them. Should be about what? What? Oh, yeah, because you got to do them separate. Ha, you're stupid. See, I told you you're going to come watch me make mistakes. There we go. Length of the first, second minus length of the first. And if you wanted to nest these together into one statement, um, we'll do this one as a 2. You would do primes of not the second of 20,000 minus the primes of 10,000. Not, oh man, you're having problems with your zeros today. I'm sure you get the same answer. Only difference is I didn't have to do all this extra typing. Okay, comments, questions? Anybody watching this? Okay, I hope so. Um, okay, so the next problem. Okay, so now here's so in the M file to get into a new section, you do a double space, the percent sign in a space, and enter, and then see how that created another space. You can also in the live editor come up here and say section break and get the same thing. Cool, right? Yeah, far out, dude. Totally tubular. Oops. Okay, and then we're going to do our text up here and say this is a problem 3.16. And this is one that students struggle with a lot because they're just not familiar with the capabilities of MATLAB. So let's look at problem 3.16. It's right here. It's boom, boom, boom. I got it. It's coming. It's coming. Here we go. I hope it's legal for me to show this textbook on a YouTube video. Holly will let me know if it's not, I guess. I hope. So 3.16 is range depends on the launch angle and the launch velocity. Here we go. The range of an object shot at an angle theta with respect to the x-axis has initial velocity v naught and is given by the range as v naught squared divided by g times the sine of 2 theta. For theta 0 to 2 pi and neglecting air resistance, use 9.81 at initial velocity. Show that the maximum range is attained by approximately pi over 4 by computing the range and changing theta in increments of pi over 100 between 0 and pi halves. You won't be able to find the exact angle. We could if we wanted to, but we're not going to. We don't learn that yet. The results in the maximum range because your calculations are evenly spaced angles of 0.100 or pi over 100. Okay, so you got all that? Cool. If not, rewind, pause, and read it. And mute me out so that you can understand it. So first off, we need to define RG, 9.81. That's given. And then we're going to have our theta is going to go from 0 by the pi, and if my daughter was here, she could give you the first 100 decimals of pi. But we're going to go by pi 100 to pi divided by a 2. And our V naught is equal to, I think it was 100 meters per second. And I suppress all my variables because I don't like them displayed. Okay, so now we're going to use the equation given to us here that says range is equal to V dot. No, we don't have to dot because that's not a vector, but we do need to knot it. Raised to the 2 divided by G, and all that is multiplied by the sine of 2 times theta. Okay, so now we have our range and we have our theta. The two are symbiotic with each other. One relies upon the other. So you haven't learned this yet, but what I like to do is when I do something like this is I like to throw up a plot of my variables here and range, and it gives me an idea of what I'm looking for. So we're going to run this here real quick, and it'll show us a nice little plot down here in the window. And I've been hitting Control Enter to make it execute. You can hit Control Enter, or you can come up here and run section. I probably ought to do that once or twice, but I just so many years of hitting Control Enter. Sorry. So it looks like our maximum here is about 1,000 down around zero point 0.8 radians. So now, how do we find what exactly, according to the data we plotted, that value is? Hey, teach, I know how. I know. Okay, you down there, the goofy looking one. How do you do it? Well, teach, what you do is, see, you take and assign two variables. And a second one is just a location that tells you where the maximum value is found, and use it on the max function. So what the output's going to be is the maximum value in this array, and this will tell you exactly where it's located in that array, or the element number. That is very good. You get a gold star. Cool. Okay. So there we go. We have it. No, we're not done yet. No, we're not done yet. Okay. So we know the maximum height. And we'll just print out the max height just because we want to display the answer to the problem. Want the time, oh, no, not time, theta. Theta at max height is going to be. Okay, so what we do now is we know where this is located within this array. This array is directly related to the theta variable, because every value in the range was created based off of a calculated value in theta. So what we do is we go find out which value in theta is in the location position of the theta variable. And that's done by saying, well, we want to look in theta and tell me what is in the location or element or spot. You can call this whatever you want. This is just what I do so I know what I'm doing. Then we're going to find out just what pi over 4, which is radians, 40 equivalent of 45 degrees, so that we can compare our outputs, not pi over 4. So this should be the same as, well, let's do this as a compare. Compare is equal to pi divided by 4. And so theta at max height should be very close to compare. So now we come up here and hit run section. And so we got our max height is 1,000. Told you it was right around 1,000. And it's thinking, what? Oh, you left the A out. See, why didn't somebody say something? I was thinking of it, but I didn't want to stop you. You were on a roll. Here we go. So we got max theta is at 7.845. Theta pi over 4 is 0.8 or 7845. So those are identical. So that's how you go about finding the time or angle or whatever variable is, this array is dependent upon how you find it using the max. Same with the min and other things that we'll come across too. Cool. Farm out, right arm. That was. If you have any questions, let me know. I will post this video. I should have it posted tonight. It's only a 12-minute video, so okay. Have fun. Let me know when would be a good time for you guys to meet. All right, ta-ta.